Patterson is a professor of geology at Carleton University, and which is in Ottawa, Canada, and he's a senior visiting fellow at the School of Geography, Archaeology, and Paleoecology at Queen's University in Belfast. He serves as chairman to the International Climate Science Coalition, and his research emphasizes the dynamics of climate and sea level change for the past couple thousand years. And he serves as a project leader for UNESCO's International Geological Correlation Program, and its charge is to study sea level changes. He's also the founder of a journal, Paleontologia Electronica. So that one he founded that, and he's published over 130 peer-review articles over his long career. So without delay, I'm going to get this published, or this one down, and then
Great, thank you. And I have to hit F5. Okay. All right, worked okay. It's Paleontologia Electronica. That's the co-founder. The first electronic paleontology journal founded in the 1990s. Oh, sorry, I have to get closer to this, sorry. Yes, a lot of competition in the room with the talks next door. Anyway, what I'm going to discuss with you today is some research that's coming out of my lab that we've been working on in the last few years on the west coast of Canada. And we've been basically looking at extremely high resolution climate records, I guess it's that button right there, that are archived in inlets along the coast. And these inlets there are characterized by, let me move on the next slide right here, they're long and narrow and deep with some sills. They're found within them, and these sills basically result in the inlets being, the deeper water parts, them being quite isolated, and they typically become anoxic. Here's just a photograph of Effingham Inlet here on the west coast of Vancouver Island. I'm not going to talk about them all today, basically due to the time constraints, but they're very deep, long and narrow, and as a result, you end up with conditions such as right here. Here shows the sills right here, the inner basins and outer basins right here. We have typical estuarine circulation that you find in these sorts of inlets, which result in the sills and the deeper water becoming quite anoxic. And because they're quite anoxic, anything that falls into the deep water of these inlets stays there. There's no biological activity going on, there's no overturn, anything like that. So anything that happens is going to be preserved there. So as a result, you get an extremely high quality record preserved for a very, very long time. I'm going to just describe a little bit what controls climate in the Northeast Pacific region before I can talk about the main event today. Basically, there's two circulation gyres. In the summertime, climate is dominated by the North Pacific High, which is a clockwise gyre, and that results in offshore Ekman transport, which results in upwelling. That upwelling brings cold, deep, nutrient-rich water, which supports phytoplankton and on up the food chain, and as a result has a big impact upon fisheries and so on in the region. In the winter, the North Pacific High retreats and is dominated by the Aleutian Low, which is a counterclockwise gyre. That results in the Aleutian Low winds going this way, and you end up with an onshore Ekman transport and downwelling, and in the wintertime, phytoplankton don't like it anyway, but they particularly aren't going to like it because of the downwelling type conditions. The other major driver in the region is the jet stream, which is going to bump around the Aleutian Low and the North Pacific High. And I love watching the Weather Channel all the time, so you get to see the cold. And particularly, I live in Ottawa, and there's a big difference between when that jet stream rides north of us in the wintertime, it's happy days out on the skating rink somewhere, but if it shifts south, we can get a nippy breeze coming around there. And so this is like a rope. It's going around the world, circling the Earth, and basically sometimes it gets stuck in particular patterns. If it gets stuck in a pattern, the Aleutian Low and the North Pacific High go along with it. And these are the sorts of records that we get. And so, so you basically collect these cores, and they're these sort of brown muds in there, and it's not kind of nondescript right there. But if you look at an X-ray that are collected here, you can see that there are lighter layers in here, which are the diatom layers laid down in the summertime, or the phytoplankton. In the wintertime, we end up with these darker layers. Again, these narrow fjords, and so you have a lot of precipitation going along, and it's washing material into the inlet. And we collect these with these. Here's a piston core right here, and here's a freeze core for getting the sediment-water interface. Basically put dry ice in there, and it freezes the side of it, and you get an extremely high-quality record. So these are the sorts of records we get. And you can see just by looking at this core right here that no 2 years are alike. Okay, so you basically end up with very high-resolution sorts of records. This one here, obviously the lighter layers right here, we can see that's a diatom-influenced one. And so you have so it's a thicker layer, so that was a great year for the North Pacific High and upwelling, and some of these ones down here where it's much thinner, those were years with the Aleutian Low dominated. So what we did, and this basically, I'm just getting a preamble right here because it's not the main thing I want to talk about today. I spoke on this conference last year about the sorts of cycles we were recognizing. When we did a time series analysis, this is a wavelet analysis right here, but we did up spectral analysis and so on. And again, to just explain for people who aren't familiar with wavelets, wavelets are a wonderful way to visualize cycles that you're going to see in a record. This is basically, imagine the core laid along here, and the X-rays that we were basically scanning to look at the signals in here. This represents shorter time and longer time, and you can visualize the various sorts of cycles that are archived within the record. And here are the longer records here. Here's the 1,300-year, 1,700-year cycles. These are the sorts of things I think that both Craig and Fred were talking about. Again, not as dynamic in the Holocene as we have in the earlier records. Again, here's a segment. This is from about 2,000 years ago back to about nearly 5,000 years ago. You can recognize shorter cycles in here. Here's one here about a 200-year cycle, which is about like the Seuss solar cycle right here, which is dominant for a little while in the middle part of the Holocene, and then it just dies right on the spot. And then basically we have new cycles appearing in here. There's a major climatic cut that I'll talk about a little bit later that's recognized throughout the region that we see in this core. And then blipping in and out are shorter cycles in here. This is the Gleisberg solar cycles that people have spoken about. So you can see at many different scales with these sorts of wavelet analysis, the sorts of events that are going on. And we saw the same thing with other proxies that were used. A lot of the research money was provided from both the Natural Sciences and Engineering Research Council of Canada, the Canadian Foundation for Climate and Atmospheric Sciences. And so part of our mandate was industrial. And so basically there's a problem on the West Coast with fisheries, that they don't have a very long fishing record, and their whole fisheries collapse. You know, not just the well-documented salmon fisheries and so on, but also sardines, anchovies, so on. And they would have a huge fishery one year and they disappear the next. And just by looking at our records, we can actually see, here's looking at both anchovies up here and sardines down here, that their populations come and go as well. And we basically were documenting the scales that we'd find in these cores. And they were also blipping in and out according to Gleisberg cycles and other cycles as well, with particularly dramatic changes during major shifts. So this is basically the sorts of things that I have described before. And the shifts can be dramatic. Here's, for example, a transition right here at 4,400 years ago, and basically this is the shift. You can see down below, from what I've just described, you have these thicker, the lighter layers in there. This is dominated by diatoms and so on. We have a lot of upwelling going on around there, so this is dominant. But the big news here is that how dramatic the shifts can be. Right here, at this interval here, we suddenly went from one regime that dominated by upwelling and the North Pacific High to one that's dominated by the Aleutian Low, in this particular case right here, and begins to have the more dominated by the terrestrial input into the inlet and not much upwelling going on. So these shifts are very, very dramatic when they do occur. And the nice thing is when you lay a core along it, you can actually see what the sediments are that what the wavelet was actually helping us visualize. And again, I'm not going to spend much time here in the well-documented now Sven's mark idea about climate change here. Basically, there's been a few ideas as to how we can have amplification of what was otherwise a pretty minimal change across the sunspot cycle of 1.4 watts per square meter. So it's been interesting since the discovery of sorts of cycles that I'm seeing, many other people seeing them as well, that there have been suggestions how that can be amplified, and this is the one I won't spend any time here, the galactic cosmic rays striking the Earth and resulting in formation of clouds, and then we have the sunspot cycle that will either, if it's at the peak of a sunspot cycle, essentially blow away the galactic cosmic rays, or during a trough of a sunspot cycle, more get through, and that's an interesting correlation. And that may be part of the story for up in my region. But something that I found very interesting was some literature that I discovered talked about other sorts of amplification that could be going on there as well, involving UV radiation. Basically, UV radiation results in the enhancement of the ozone layer by producing some ozone. And as we move across a sunspot cycle, as you move to the peak of a sunspot cycle, there's something like a 0.4% increase in solar UV radiation. And that influences the ozone concentration, of course. It makes more of a greenhouse gas, which is going to have an impact upon radiative heating. But of real interest to me when I was reading these was the idea that it had an impact upon zonal circulation. And that increase would result, it starts to influence the jet stream. And the jet stream plays, as I mentioned before, a big role up in my particular region. So it starts to kick it down from the stratosphere and the troposphere. And again, it's like a rope. So that rope is being modified a little bit around there, and that starts to influence other weather patterns that the jet stream is going to influence. And so what it's doing down here is there's an instantaneous pathway on up into the Northeast Pacific, influencing the North Pacific high and the Aleutian low. And so this, the model that, and this has been documented, and here's a couple of papers have appeared that have actually tracked the center of action of both the Aleutian low and the North Pacific high. The center of action is where these seasonal gyres form every year, and they migrate according to where the sunspot cycle is. And so they're migrating east and west. During the solar minimum, the Aleutian low will migrate to the eastward, and the North Pacific high starts to migrate southward during a minimum, and the opposite during a maximum. And so these little dots in here show the various centers of action changes over time. So the model that we had was talking about the sunspot celestial solar modulation going on, which will have an impact upon circulation anomalies, perhaps clouds. I don't know how that would fit into our region, which displace the jet stream and the troposphere and stratosphere, which is going to start moving the North Pacific high and the Aleutian low around up to 700 kilometers, which is going to enhance or unenhance, depending on where it is, the diatom production, and which is going to impact upwelling and so on. And this is what we see in our records up in here. So depending on where those winds are coming from, according to where we are in the sunspot cycle, and the relative influence of the Aleutian low and North Pacific high, it's going to impact the thickness of the bands that we're seeing. And so that's sort of a direct pathway. And then when we do scan these cores that we have, then we end up seeing these patterns preserved. So that was all very interesting. And this is what I spoke to this audience last year about. But we have other major climatic phenomena that are impacting this region as well. And we've already heard about it from both Fred and Craig, things like the Pacific Decadal Oscillation. How does that all fit into it? So the Pacific Decadal Oscillation, as we've already heard today, is they're sort of like an El Nino, but just the opposite, and very long-lived sorts of events. They're most dominant up in the northeastern Pacific region, and they have a couple of major periodicities, one in the 15 to 25 years and one in the 50 to 70-year range, and they have been demonstrated to be correlated with each other, sort of phase relationship. And there's been, and again, I won't spend much time here because we've already heard about this today, there's this PDO index. How they measure this is basically looking at the variability northward of the pole from about 20 degrees northward from 1900 to 1993, and this is basically looking at their positive phases and negative phases as they jig back and forth. And in the 20th century, for example, there was two of them, a cool one from 1890 to 1924, and another one from 1947 to 76. A warm one from 25 to 46, and from 1977 through the 90s, and then on to what we've heard about a little bit earlier, but what the PDO's been up to. Now I'd like to, today's talk, basically, after all that preamble in there, to talk about, well, is there any sort of correlation going on then between these solar cycles that I was recognizing before and the PDO? And we've already heard some hints about that already today, about how these correlations might be going on. This is a longer core from Effingham Inlet called MDO22494, which reaches back basically through the whole Holocene in here. And wavelet analysis has been done on percent opal in here, which is basically looking at silica production in here, and through this whole interval. And I just draw your attention here to bands at this wavelet at about the 90-year cycle, which is about the Gleisberg cycle, as well as in the shorter bands, the 70-year on down to the 20-year bands in here, which look at the various bandwidths of the Pacific decadal oscillation. And through the balance of the talk, I'm going to concentrate mostly on this latter part from the middle Holocene on up to more recent times. I'm also going to, as part of my story, talk a little bit about sea surface temperature reconstruction, because basically we're going to have a look at these changes that are going on perhaps with PDO and Gleisberg cycles in the context of what climate was doing in this region from the middle Holocene on. And to do that, we did a reconstruction of sea surface temperature in the region, and this is just basically a diagram right here showing Northeast Pacific sea surface temperatures, and you see there's quite a variation as you move from north to south, and in the wintertime it gets down as low as 4 degrees Celsius on up to 11 degrees Celsius. So the winter sea surface temperature is quite variable, and actually a pretty good proxy for what's going on. Summer's not so great, mainly because it's an upwelling regime and you don't have a lot of variation going on, so it's cold. It's cold water coming up, so it doesn't change so much from the winter. So the winter sea surface temperature is a very good proxy. Here's what we did for the sea surface temperature proxy. Used dinoflagellate data, basically, which are sort of like diatoms or producers in the ocean, and looking at modern day distributions and what's controlling productivity, their sea surface controls and various other sorts of parameters out in the surface sediments from the Gulf of Alaska on down through to California, and comparing them against dinoflagellate data from a couple of cores within Effingham Inlet, and also looking at some distributional data of these dinoflagellates within inlets and so on throughout the region as well. And this is how we developed our transfer function. And this is the transfer function, okay? So basically you're reconstructing temperatures. This is in degrees Celsius from the present time on back to about 5,500 years before present. This is for one of the cores, TUL99B03, looking at the sea surface temperature variation here, and here is for TUL99B11. So I'm going to spend the balance of the talk then discussing what the significance of these changes might be. There's an interesting history here in the middle part of the Holocene around here. Conditions were relatively warm and dry if you're looking from a continental context around here. Basically, from the early Holocene, insolation was quite high, and as a result, it was that ended up with the North Pacific high tended to be a little bit further north in the middle Holocene than it is at the present time. The Aleutian low is further west, and so the region was dominated by this North Pacific high, which resulted in very strong upwelling throughout the region. And it tended to be sort of a PDO negative sort of event. There was a big change occurred here right around 3,500 years before present. And again, this is a little excerpt from core TUL99B03 right here. Looking at this change, we had what was dominated by the sort of a Seuss cycle type of domination. The bandwidth changed, the frequency changed very, very dramatically around here, whereas we had things like the longer bond cycles just carried on through, and some Gleisberg cycles going through. But there was a big change went around here that we can see quite clearly around here. It was marked by dramatic temperature sorts of changes. As we moved on into the later part of the Holocene, after 3,500 years BP, and again, this has been documented throughout the region, the Aleutian low started to become more dominant. It started to move into the position, the late Holocene position that's been in generally. The North Pacific high began to retreat more to the south, and that resulted in generally weaker upwelling and neoglacial advances moving throughout this region that have been very well documented, and these have been also correlated with global glacial advances that have been going on, various sorts of cold episodes throughout this region. So we can correlate little spikes down in temperature here with ones been recognized elsewhere, and here's another one going on here. Also going on with that, the California current, which is marked right in here, because they were being influenced by the atmospheric gyres around here, that began to weaken off. And as that weakened off, the central gyre that's out in here in the Pacific began to migrate shoreward. And when it began to migrate shoreward, it resulted in overall sea surface temperatures begin to come up. throughout that region. And we began to end up with more El Nino-like or positive PDO type of conditions. And I just want to show you on this diagram where we're at in this sort of situation. This is the transition right here from the late Holocene from the middle up into the late Holocene right here. Here is this domination of this sort of Seuss cycles around in here. There wasn't much in the way before that at that interval of things like the Gleisberg cycle or any of the PDOs that went along with it. But as we start to move into the later Holocene, the Gleisberg cycle began to be quite dominant. But I also point out that we began to have along with it a lot of the PDOs. The PDOs really weren't there that much before that for long intervals, and they began to appear. Then as we moved into through this colder episode, about 1100 years BP, or about 900 AD, we had what is known as the medieval warm episode began to appear, or warm period. And interestingly, in this core, we see the same sorts of things that we began to see in this one as we move from the middle Holocene to the later Holocene, that the reappearance of this longer wavelength Seuss cycle type phenomena start to appear in here. And we begin to actually have in here our Gleisberg cycles, which had been around here before, they begin to disappear again, as well as some of the longer wavelengths of the PDOs that went along with it. So the sea surface temperatures through this medieval warm episode, they begin to die off. We begin to have the North Pacific high shifted northward again. The Aleutian low began to shift west. And we began to have higher, it was just like back in the good old days of the middle Holocene again, we began to have these higher productivity sorts of situations go on, the stronger California current developed, and things became warmer and drier again. So it's like we were, for a short period of time, for a few centuries, returning back to what conditions were like in this region earlier in the middle Holocene. And we can correlate that now, but at this stage, with things that were going on continentally. Here is a medieval warm period. This is looking at these famous North American medieval mega droughts that have been recorded in here. And they were characterized by long periods of very, very extensive droughts that made the droughts of like the 1930s and so on in the late 20th century look like pikers. And they basically did, as you probably heard, the Anastasias and so on, their civilizations disappeared and had impacts elsewhere throughout America. And so these were characterized, prolonged and pronounced negative PDO intervals going on in here through this interval. Then as we moved on into the Little Ice Age around in here, the sea surface temperatures begin to flatten out again around here and remain cool. We begin to have generally positive PDOs in the Northeast Pacific. The Gleisbergs came back again, and that was also characterized by the less arid and terrestrial conditions are going on. Again, we can see this sort of thing happening here comparing with the wavelet analysis. And then finally, the last bit of the record right here, as we move on out of the Little Ice Age and on into the 20th century warming that went around here, we began to have an increase again in sea surface temperatures around here. The positive PDOs in the Northeast Pacific, because we actually have now thermometer records of these going on, and again, the return of increased arid and terrestrial conditions, sort of like what was going on during the medieval warm period. And so here's just, again, this record in here at much higher resolution than what we're seeing, just so we can see this general pattern here. And I'm not the only person to see these sorts of things. Here's an interesting paper by Shin et al. In Geophysical Research Letters, and they found a very close correlation when they did cross-spectral analysis and wavelet analysis between the Gleisberg solar cycle and the PDOs. And this is looking at reconstruction of summer rainfall. Again, this is the other side of the Pacific in eastern China. And they found basically then the PDO was a persistent feature, which was with these sort of phase-locked oscillations, but it was very closely correlated with the Gleisberg cycle. And they suggest that the Gleisberg solar cycle then controls the major rhythm of the PDO in their interval. You know, they didn't have that long a record, it was only going back to 1500, but during the Little Ice Age, it made a major control over the PDO. And so the suggestion is that perhaps the winter sea surface temperatures that we have in Effingham Inlet, basically, they're going to help us a little bit understand our relationship between northeastern Pacific paleoceanography and the terrestrial record more and supplements that data. But I think what's very interesting is that very high productivity marine regimes and terrestrial drought intervals are characterized in this region by this 200-year de Vries or Seuss type cycles. They're very, very clear in the data that we have around here. We also have these Gleisberg cycles that blip in and blip out through this entire record around here. And they are in varying intensity and very robust features when they come and when they go. It's when the Gleisberg cycles are absent or weak, the PDOs are going to be weak along with it. When the Gleisberg cycles are strong, we end up with the PDOs of varying intensity. And again, it's a nonlinear relationship, so the PDOs aren't always going to respond. But the idea here, I think, is that this Gleisberg cycle, which is the solar cycle, in which there's all these different solar cycles around here, these are sort of the pacemakers. And so these pacemakers that are going on in the ocean, they control the natural rhythm of the ocean, and then the PDOs are riding over top of these. And these riding over top of these, and so that provides the pace, and so the PDOs are going to come and go, but without that pacemaker underneath it, they're either going to disappear for long periods of time or they'll be present. So anyway, that's, I think.